All right, so you guys can hear me, see me?
Yes.
You can see my screen also? Yes, I can hear you
Yes.
clearly. All right. So in the previous class, we were talking about concepts of effective length for lateral torsional buckling in beams, right? So the one table we had discussed was table number 15 in IS 800. This table is basically for simply supported beams. Likewise, there is a table, another table, table number 16, which is for cantilever beams. Yeah. So this is table number 15, and this is table number where these tables are. So table number 15 is on page number 58, and table number 16 is a bit later on page number 61. Okay. Now there are some corrections to be made in both these tables. In the first table, table number 16, because I'm at this table right now, I'll talk about it. At this location where it says top restraint condition free, and it shows a small piece of metal connecting the beam to a brace, right? So this is my beam and this is a brace, and you can see a connection between the two. If it is free, that brace and this connection should not be there. Yeah. So please remove this brace, this lateral member, and this connecting member. These two should not be there. The beam is free. Okay. That is a correction to be made in table number 16. And table 15 also had a mistake. Last time I had talked about it. If you see in table number 15, read the third column, that is warping restraint values written for the first row and the third row. The first row value says both flanges are fully restrained, and third row also says both flanges fully restrained. So basically first row and third row are completely identical, but their corresponding effective length values are different. In the first row, the effective length is 0.7 L, but in the third row, the effective length value is 0.8 L. So there is a difference. And there is obviously a mistake here. So the mistake is in the first row. The first row says warping restraint is both flanges fully restrained. It should be both flanges partially restrained. Please correct it. Both flanges partially restrained. Yeah. You can download the addendum to this code from the internet. This is the addendum, and it says it gives step page wise what are the problems. Okay. So there are several issues. There is a long list of corrections in IS 800. Please make sure that you refer to the correct version. Okay, that is understood, right? Okay, and so we had talked about different types of torsional restraints, how to provide different types of torsional restraints I had described in the previous class, and how to provide different types of warping restraints. So warping restraints are basically in a way to, let's say you have a flange ends, so you have the beam end and you have some way to restrain its warping. So basically the idea is that when warping takes place, where then one flange bends this way and the other flange bends this way. So if you can prevent these two flanges bending in different ways, and there could be ways to do that. One very effective way is to put a very thick plate, weld the thick plate at the end of the column. So sorry, at the end of the beam. So if you do that, that will effectively restrain warping. Okay. Similarly, there are ways to restrain torsion. So one way is again to provide braces. We had discussed in quite a bit of detail how to restrain torsional movements. How do you do that? You basically connect with bracings both top and bottom flanges, right? So if you do that, then very effectively you can restrain torsion. Alternatively, you can restrain partially. You can restrain torsion partially. What you can do is where the beam is resting. So beam must be resting on somewhere where the support is. At that location, if you tie the bottom flange on both sides completely to the support, so you can provide some bolts or something. So to tie the bottom flange of the beam with the support, then you can partially restrain the so that would qualify as partially restrained by bottom flange support connection. Okay. Similarly, the last one, partially restrained by bottom flange bearing support, that is just by placing the beam on a support. So just because the beam is resting on a support, it inherently has some restraint against torsion. So even that can be accounted for, right? So these were the different types of torsional restraints and different types of warping restraints. In addition to that, there were two other challenges or complications that we had to understand. One was normal type of loading, another one was destabilizing kind of loading. And the difference between normal and destabilizing kind of loading was explained here in this slide, right? So we had again discussed this thing in quite a bit of detail. So if the load, because even though we derive the moment equation, the buckling moment equation for a uniformly applied moment, which is basically equivalent of no gravity loads acting, because if you have any gravity loads acting, you don't have uniform bending moment. But reality is that whatever moment we are getting would most likely be coming from the gravity loads, right? So if the loads are coming, which may be distributed loads or which may be concentrated loads, depending on where they are acting in the depth of the beam. So if the loads are acting away from the shear center, then it does not introduce a destabilizing effect. But if it is acting towards the shear center, then it adds to the destabilizing effects and it makes the beam more vulnerable in lateral torsional buckling. And in such cases, you have to take different effective length values, right? That part is clear, I suppose, right? Now, moving forward, for cantilever beams, similarly for cantilever beams, we are allowed to use the same equations that had been developed for simply supported beam. Okay, so now you must understand that cantilever beam is fundamentally different from a simply supported beam, and its buckling equation would be very different. But what the code is suggesting is that instead of using one L, if you use a larger L value, yeah, then you can probably use same equations for cantilever beams also. So let me go to that page. So depending on what kind of constraints are applied, you can use different L values. So for example, if you have the nomenclature in this particular table number 16 is a bit confusing. It says restraint condition, it says at support, and then it says at top. And basically what it means is that at support is where the lateral support is available, and at top is where is the farthest end of the cantilever, is the free end of the cantilever. So that end is free for vertical movement. Now what you're talking about is lateral restraint condition here. So at the top, that means at the free end, whether the lateral movement is free, whether the lateral restraint is provided only to the top flange, whether the lateral restraint is provided, only torsional restraint is provided at that free end, or lateral and torsional restraint are both provided. So what you can see here is, in this particular case, now they have shown two beams and it makes it very, very confusing which one is actually the beam and which one is actually the restraint. So to clarify where they are writing L, that is the beam of our interest. Okay, so that is the beam for which we are designing, and we want to know what is the effective length value. So this is the cantilever for which we are designing. Okay, so in this cantilever, this is the place which is at support. This location is at support, and this location is free. And for the free location, or sorry, at top. So this point is at top, and this point is at support. And at top, you have to look for free or lateral restraint to top flange, torsional restraint, and lateral and torsional restraints. And how do you do that? How do you get a free condition, lateral restraint to the top? Those all are described here. So free means free. So that means this connection is not there between the beam and the brace. The other one is laterally restrained to the top flange, or otherwise you may have torsional restraint. That means both the top flange and the bottom flange, they are effectively connected between the subsequent beams, right? And lateral and torsional restraint. In this way, these braces are continuing beyond. That means they are providing a lateral against lateral movement also. So it is not against, it's not only restraining the torsion of the beam, the lateral movement. Okay. So these are the four boundary conditions available for the free end. And then there are four boundary conditions available for the fixed end. So at the fixed end, you may have lateral restraint, at the fixed end, you may have some kind of a restraint which is providing lateral restraint to the top flange. Then you may have situation where partial torsional restraint is provided to the fixed end, to the fixed end. you may have condition which is looking like this, where some connections are provided, bolted connections are provided with lateral and torsional restraints available at the fixed end, and you may have a condition where it is, yeah. And based on these, and plus based on whether the loading condition is normal or destabilizing, different effective length values are available, and those effective length values need to be used, LLT have to be used in the beam buckling equation. So in the M critical equation, you remember this? Here, in this M critical equation, that LLT value needs to be used. Okay? Any doubts? Any questions or doubts on how to calculate LLT? Okay, fine. I'll move forward then. So now there are a couple of assumptions that we had made in that process, and we have to address those and see what the effect is, right? So, sorry, excuse me. One was we had discussed this before also. In the assumption in the derivation of M critical, that is elastic lateral torsional buckling moment capacity of a beam, it was assumed that bending moment through the length of the beam between the supports is uniform. Correct? Now that is of course not almost always untrue. That's almost always not valid, and in practical situations, moment is always varying. However, we discussed this in the past that it's a conservative assumption, correct? So, however, even though it's a conservative assumption, sometimes you may find that engineers would not want to be so conservative and they would want to be more accurate, because unnecessarily, why are you wasting material? If you can manage with a smaller size beam, why should you go for a large size beam? That is just kind of a approach. So Indian code allows you to be more accurate in calculating actual buckling moment capacity, but that is not part of the main code. That is in one of the annexures. So you need to go to annexure number, annexure E. Okay, this one is annexure D. So if we go to annexure E, here the code allows us to calculate the moment capacity for a varying type of bending moment, right? So for example, what it says is that if this is the load on a simply supported beam, or if this is this kind of boundary condition, then the bending some C1, C2, C3 constants and K constant for this type of different types of bending moment diagrams. Likewise, various types of bending moments diagrams are available, for which you can take the values of K and C1, C2, C3, and then use them in some equations that are given here. So these equations, for example, this equation here on page number, page number 128. So this equation allows you to use, it has a K value, KW, C1, C2, C3 values. So you can substitute those values here, and you can try to get actual maximum bending moment at which the beam would undergo lateral torsional buckling. Okay, so instead of using that formula that I have discussed before, one can use this formula also, which will allow you to calculate the M critical value more accurately, which will not be as conservative, but it will be more efficient. Okay. Also, if you may remember, the expression for M critical was derived only with singly symmetric or asymmetric cross sections. Sorry, doubly symmetric cross sections. So I'm sorry, the M critical value was derived for doubly symmetric cross sections, right? So what happens if the beam is singly symmetric or asymmetric? Then again, the same annexure E gives you another set of formulae. So this is the same formula that you are familiar with, which is valid for doubly symmetric cross section, but this this formula, again the same formula that I've just discussed, it allows you to calculate M critical for a cross section that is symmetric about minor axis. Okay, so cross section that is symmetric about minor axis. Please pay some attention to it. So what does that mean? What kind of cross sections does it allow to be used? Let me open a so if I have an I section, it is doubly symmetric, right? This is a doubly symmetric cross section, there is no issue. What happens if I have one flange thicker than the other flange? Thicker and wider than the other flange, which is a very common type of beam design. And in this kind of a cross section, this is singly symmetric, clearly, right? So whether it is symmetric about minor axis or it is symmetric about major axis? Somebody please answer.
Minor
Very
axis.
good. So this axis is the major axis. It is not drawn at the right location, but I hope you take the point. It will be slightly shifted upward. So this is the major axis and this would be the minor axis. Okay, so this cross section is symmetric about the minor axis. So such kind of cross sections will be can be taken care of by this method. Similarly, if I have, so T section is also, so T section also comes under the similar classification. Okay, so all such cross sections, even a this kind of a cross section, box section, which is not symmetric about both axes, but symmetric only about the minor axis. So such kind of cross sections will come under this classification, and they can be this equation can be used again for calculating M critical value of such cross sections. Okay, which was not possible with the original M critical value that I had discussed in the earlier sessions. M, but for only this one, it can be used. Now, even after this also, it cannot be, this equation is also still not valid for some other cross sections. For example, if I have this T section, or if I have this, let me ask you a question. If I have this channel section, it is symmetric about which axis?
Major axis.
So it is symmetric about this axis, right? And that is the major axis, correct? So a cross section like this, which is symmetric about major axis, can we use this provision?
No.
We cannot use it. We cannot use this provision. We cannot use the earlier provision also. Similarly, if how about this one? So this is a beam which is supported like this, and the beam is spanning like this way, and then it is extending, and then there is another support on the other side. Okay, so you understood, right? So for this kind of a beam, how do we calculate M critical? This is symmetric about the major axis, but bending in the minor axis. Anybody? This is a trick question. The answer is somewhere else. Yes or no? Okay, so we don't know. The answer is n critical. We don't know.
We
The
need to
method does not help us. Yeah,
use the
sorry. Go ahead.
same equations as we use for I section, since we don't have any method in IS code.
Yeah, but those equations are not correct. You may use it, but then you are on your own because you don't know whether the values that you are getting are anywhere near the correct values or not. Okay.
Yes.
But funny part is that you don't need MCR for a member that is bending in the minor axis, right? You forgot that. If you go to this section, that is 8 point, sorry, where is 8 point? Let me go. This one, 8.2.1. So we need to ignore, we can ignore lateral torsional buckling if bending about weak axis or the minor axis. Right? If the cross section, if the member is bending about the weak axis, then we don't need to calculate LTB. We can ignore the lateral torsional buckling. That is true for this case as well. So this kind of a member under gravity loads will be bending about the weak axis. So we don't have to worry about M critical. We don't know how to calculate M critical, but also we don't need to know for calculating the bending moment capacity of this cross section. Only the yielding limit state will govern. However, for this kind of a cross section, lateral torsional buckling is very much a possibility, and we don't have an equation in IS 800. Some international codes have equations. You can use those equations, but Indian code does not have an equation for such kind of cross sections. Okay. It has equations in section 8. You can use this. Annexure E you can use for this kind of cross sections. But for these kind of cross sections, you don't have any equations available in the Indian code. For this one, you don't actually need any because lateral torsional buckling does not take place. But for this one, you do need, but Indian code does not help you. You can go to international codes and find a value. All right. AISC code you can use, Euro code you can use. There are various codes available. All right, we'll move forward now. So with this, I suppose we have completed the discussion on the bending moment capacity of beams, mostly, right? Most of the important things that we needed to discuss. One thing that I had discussed very briefly in the beginning was the shear capacity of a beam, and we had said that you calculate shear capacity of a beam by assuming that only the web carries most of the shear force, and you know at what stress the web would yield in shear, and that's how you use it, right? So, and it was required for us to also calculate the effect or the interaction between the shear force and the bending moment capacity. So I'm just recapping that again because in case you did not understand that fully last time. So what you see here is so if you have a rectangular cross section like this one, then the shear force diagram varies like parabolically here, right? And do you understand how does the shear force, not the shear force diagram, sorry, shear stress to the depth of the cross section varies like this parabola, right? So the maximum shear stress is at the neutral axis, and on both sides it is less than that. Okay. Why does it vary like a parabola? Can anybody give me a physical meaning for this, physical reason for that? Why does it, not necessarily parabola, but at least why is it reducing as we go up and as we go down? Anybody?
It is directly proportional to moment of area about neutral axis. That varies as parabolic. So the shear stress varies parabolically over here.
You are right in the way that you have just explained this expression given above. That is, in this expression, shear stress is equal to A multiplied by y bar. And if you see the value of y bar, that is the distance of an area A, which is hashed here. If I want to calculate shear stress at this level, I will take the area on the outside of that line. Okay, so if I want to calculate stress here, if I want to calculate stress here, then I'll take area outside of that. Yeah, and that area multiplied by the distance of that centroid, that area centroid from the neutral axis. That is okay. So this is the expression. But physically, do you have any sense of why it should vary? Why it should be highest at the centroid and or at the neutral axis and smallest farthest away? Okay, let me try to explain. Yeah. So let's say I have a rectangular section, and there is a small strip in the middle of this section. Now this section is basically the cross section of a beam that is extending. Okay. Now looking at this beam this way, which is supported between two locations. One second. So this is that beam, and let's say there is some kind of a shear force diagram. Uh, let me take a simple case. So let me say that it is having a distributed load. It is resisting a distributed load. That means there is a shear force diagram which looks like this, and there is a bending moment diagram which is parabolic. Okay, and I'm looking at a particular location, and maybe I'm looking at a particular length of this section. Yeah, so I'm looking at this length of this B. I'll call this point A and this point B. Fine. That A point is right here, and that point B maybe point B is here. Fine. And the same strip that I had that extends from A to B, and it exists at point B also. Now, as you can see, that bending moment at A is less than bending moment at B. Agreed? So what does that mean? That means that the corresponding stresses at B will be also higher, right? Which are the corresponding stresses? Flexural stresses, which are axial stresses, basically longitudinally, right? So if I take these longitudinal stresses at A, and since it is on compression, it is in the top. I've taken this strip at the top. These are compression. So compression forces are acting at A at this strip, and there would be compressive forces acting at B also, right? And the compressive forces at B are larger than, I'll call it FB, I'll call it FA. So FB is larger than FA, isn't it? Any doubts so far? So now if you look at only this strip, in that strip, I'm drawing only that strip now. There is a stress FA acting here, and there is a stress FB acting here. FB is larger than FA. So how would this be? How would this strip be in equilibrium? On one side you have higher force, the other side you have less force, right? So it is not in equilibrium unless there is a additional force acting. And where would that additional force be coming from? That additional force will be coming in the form of shear stress between the subsequent strips. So let's say there is another strip right under this strip. There is another strip right under this one. So what will happen is that this strip, so what has to happen is, since FB is larger than FA, this upper strip wants to move outside, outward in this direction, unless it is being resisted by the lower strip. So what will happen is that this one at the, if I can draw the lower surface of this plane, there will be stresses acting at that lower surface in this direction. Okay, and these are shear stresses applied by the lower strip. So the lower strip is observing the same shear stress in this direction. Agreed? Similarly, this strip on its top surface would be observing a stress in this direction. Correct? Now, how much of this stress, or how much will be this stress? This stress will be basically, because there is another strip on top of it also. So there will be a stress coming on here, and then shear stress here, and there's shear stress here. So this shear stress here will be a summation of all those shear stresses. That is basically the resultant of this axial stress difference. Agreed? There would be similarly, like here there is a difference between FA and FB, there would be a difference between here and here, and that difference has to be supplied by this shear stress. Similarly, the difference here has to be supplied by this shear stress. So the shear stress here will be supplying the stress difference of this strip as well as this strip. Similarly, if you go one step lower, the strip here will be supplying the shear stresses or shear forces. The shear forces at this level will be supplying the force difference between this and this for the 3 layers. Correct? So as you keep going down towards the neutral axis, you will see that the shear stress keeps accumulating. Okay, and as a result, until the direction of these forces changes, which changes at the neutral axis. So that's how the shear stress keeps increasing as you go from the extreme edge all the way to the neutral axis. The question is, we are talking about one type of shear stress, and the shear stress that we were looking at here in this presentation is of a different type, right? So these shear stresses are acting in the longitudinal direction, but the shear stresses that we are talking about there are in the cross section, right? So now if you see, if you have understood shear stress behavior properly, you would know that the two shear stresses are nothing but the same. So if I take a small cube here, if let's say I take a cube and I'm looking at this surface, this hashed surface. So this is that hashed surface. Okay. Now the top was observing a stress in this direction, and the bottom was observing, sorry, the top was observing a stress in this direction. I did not draw it here. That's why I got confused. And the bottom was observing a stress in this direction. In order for this surface or this cube to be in equilibrium, corresponding shear stresses have to exist on the side surfaces as well. Agreed? And these are those stress. So basically what it means is that there will be stress here, and likewise there will be stress on the surface behind, and these are those stresses, and these are the stresses that are in plane stresses, and these stresses will also be same as the longitudinal shear stresses, and therefore they will also be maximum at the neutral axis. All right, I hope it is clear to everyone. Please let me know if it is not clear. Fine. Okay, so from there we can understand is that that's why we got when you said that the shear stress at a level is proportional to a y bar square, so which is saying more area you have above it, all that axial force difference. So if you have more area above it, that means the axial force difference in that area will be larger, and that multiplied by that distance will give you it will be proportional to that uh, uh, value, shear stress here, and that's how you get this parabolic profile. Okay. T, it is first you get the total force and then you divide by the thickness, and because of this T value, because all that shear force has to be transferred by that small thin sliver of web here in this case. So in case of a rectangular section, you get a perfect parabolic profile, but in case of an I section, you get a parabola adjusted for the thickness. So it would have been a perfect parabola, but since you have variation in thickness, where you have very small thickness, your shear stress values jump suddenly because it is divided by the T value here. So that's why you have a sudden jump in the shear stress value. And as a result, for I sections, we can make this assumption that most of the shear stress is carried by the web alone. Okay. And what we do essentially is, that instead of, and then in the web still there is some variation in the parabola, but now the difference between this value and this value is not very large, unlike here. Here the values were completely different between at the centroid with respect to at the ends, but here the two values are relatively similar. So what we usually do is we take the average value, average shear stress value, and what we do is basically we divide the total shear force with the cross section area of the web, and as a result we get average tau value, average shear stress value, and that we compare against the yield stress. Okay, that is the capacity of the cross section. Is that part clear? For a rectangular section, however, what we do is we know that average is actually average is taken as tau max is taken as 1.5 times the tau average. So first you calculate tau average. So tau average will be something like this, and maximum will be 1.5 times tau average. So if you are designing a rectangular cross section, which is not very likely, but if you are doing that, then you need to check for 1.5 times tau average. So you know the V value, V by A is tau average. So 1.5 times the tau average is this stress, and make sure that that stress is less than the yield stress in shear. What is the yield stress in shear? We have discussed this several times from the very first few lectures. Fy by √3 is the um, yield stress in shear as per the Indian code. Okay, and what we do is when we design Vd is equal to Vn divided by gamma m0. Vn is basically your A shear, whatever area is available for shear, Fy divided by √3, and A shear is calculated differently for different sections. So you have to look for the web, but if it is a hot rolled section, then you take the entire depth of the cross section multiplied by thickness of the web. And if it is a welded section, then you take only the depth of the web. So let me explain. If it's a hot rolled section, like this one, then we take this cross section area. Okay, and if it is a welded section, then we only take this cross section area, this area, as the shear area of the cross section. Understood? So this distinction we make because we are not sure how much of shear stress can be transferred through the weld, and that's why we take smaller area in case of a welded section, and in case of a hot rolled section we can take the full cross section, full depth of the cross section. Okay. If the cross section is bending in the minor axis, that is if it is an I section which is placed like this and then the load is applied, in such a case the actual web will not be acting in the shear. What will be acting as shear component? The flanges. Correct. So flanges will be resisting most of the shear. So basically you take width of the flange B times TF, thickness of the flange, multiplied by 2 because there are 2 of them. Yeah, and that is taken as the AV value. All right. Any doubts? Okay, moving forward. So we have discussed the design for shear. Now there is another possibility of another type of failure possible in flexural members, which is known as shear buckling of web. Now you may remember that we had designed when we were designing the yield limit state, designing the I section for yield limit state, we discussed the local buckling of the flange and local buckling of the web, right? Because when half of the cross section undergoes compression, the part of the web will also be undergoing compression, and that part of the web can undergo local buckling, right? But that is a different type of a buckling. This buckling that I'm talking about here, shear buckling of the web, is of a very different kind. What I'm talking about here is the following. So if I have a beam, this is one flange, then this is the web, and this is another flange. Okay, so and if let's say there is some shear force acting, some shear force is acting on this web. What may happen is if you take this small element somewhere here, there is a shear acting here, and of course this shear has to be compensated by, to keep this element in equilibrium, by another set of shear stresses, right? If you imagine and if you reorient yourself by 45 degrees, what you will see is that this shear can be represented as a tension here and a compression here, right? Just by this is just Mohr circle transformation. You are familiar with this transformation. Just need to use Mohr circle to get these stresses. Okay, and if you look at these stresses, you would notice that for this plate, there is one orientation where it is undergoing compression. Okay, and whenever it is undergoing compression, it may undergo local buckling. Correct? Sorry, it may undergo buckling. So what ends up as a result, if the web is very thin, what may happen is this buckling means this plate will bend like this, right? So what you will end up getting is somewhat like ripples of this kind. Okay, and you will get a deformation in the beam. Sorry, my drawing is very poor here. Very difficult to draw. So beam will undergo very large shear deformations, and there will be these kind of ripples forming in the web. And here you can see some pictures of this kind of a deformed shape. So this is a plate that is subjected to a shear like I have described, and under that shear, what happens is that you get this diagonal ripples forming, diagonal creases forming in the beam, in the web. Okay, and this is again another limit state which is not allowed. You are not allowed to have the beam web undergoing this kind of a deformation. So the Indian code in clause 8.4.2, the Indian code restricts the value of d by tw to 67, right? So let me go to 8.4.2. Here. So it says d by tw against shear buckling. So the beam web should have a resistance against shear buckling, and the d by tw is limited to 67 epsilon. If the web does not have any stiffeners, if the web has stiffeners, I've not talked about stiffeners yet. What you may have is some kind of a angles welded or bolted to the web at regular intervals, some kind of stiffeners. One second. Some kind of different members welded to the, excuse me. One second. I'm getting another Google call. Sorry. So this kind of a buckling can take place, and if you provide some kind of stiffeners, then this buckling resistance improves, and that's why we can limit this value. Okay. All right. So I think I should stop here now because I have to attend another meeting, and I'm getting already the calls. If you have any doubts, you can ask now. Maybe I can wait for 2 minutes. Okay, one thing I wanted to comment, that d by tw is basically the depth versus the depth of the web divided by tw, and that should be less than 67. So if I look at any of the ISMB cross sections, let me quickly go to one ISMB cross section, hot rolled sections. So if I take ISMB 400 for ISMB 450, ISMB 400, this is ISMB 400. Here the d value, the total depth is 400, so I can assume thickness of the flange is 16. So 32, 400 minus 32 is 368. 368 divided by 8 point, sorry, 8 point, divided by 8.9. How much will that be? 368 divided by 8.9. That is 41, right? So for ISMB 400, we found that d by tw is only 41, which is much lower than 67, right? So that most of the IS 800, almost all the IS members that are available in this one will always satisfy this requirement. So you don't have to really worry about this requirement for your hot rolled sections. Only when you go for a built up section where you weld the plates together to make your cross section, then you have to really worry about this limit. Okay, but when you get a problem to solve, you have to check that this value is satisfied. All right. So I'll stop here now, and we'll start with composite beams in the next class. All right. Thank you.